So this video, we're going to look at what favors the SN2 reaction. And let's just take a minute to look back at the mechanism that we drew when we were discussing stereochemistry. So one thing we noticed is that the nucleophile attacks the LUMO, which is an sp3 hybridized sigma star orbital. So that means to do SN2, we must have an sp3 hybridized atom. So that's one thing we have to have. So we must have sp3 hybridized electrophile. So that means we're not going to do SN2 with any sort of sp or sp2 hybridized atom. So we can't do an sp2 on, we can't do an SN2 on an alkene, on an aromatic ring, on an alkyne. It has to be an sp3 hybridized atom. Okay, the next thing that we need to do when we look at the SN2 mechanism is that we need to recognize that unlike the SN1 where we have the carbocation formed, and so it's pretty easy for the nucleophile to attack from either side, this nucleophile is having to get all the way in to where the carbon is, and these groups here are sticking out. Now here I have hydrogen atoms, which are small, but if these groups were large, it would become increasingly more and more difficult for that nucleophile to get in there. So one of the things that is going to favor SN2 is having, I guess we'll call it small sterics or low sterics maybe, and also low substitution of the substrate. And just to clarify here with the electrophile, this is the substrate. Okay, so that means if we have a methyl or a primary sp3 hybridized atom, where here we just have the hydrogen, or with a primary, maybe we have a methyl group or an ethyl group or something, and then we have the leaving group. So for both of these, the nucleophile getting all the way into that carbon to attack isn't so very difficult. All right, but once we get to secondary, you can immediately start to see that even if these are just methyl groups, and especially if they start to become larger groups, that it starts to get a lot more crowded, and it starts to get more difficult for the nucleophile to get all the way into that atom. And once we get to tertiary, it becomes really, really difficult. If you were to build a model or to look at a space-filling model of like tert-butyl chloride or whatever, it's going to be really hard. I'm just going to kind of draw like this, like it's like a shield almost, like it's an electron shield where it gets really difficult for that nucleophile to be able to get in there. So generally speaking, we're going to assume that with tertiary substrates that we're really not going to see much, if any, SN2. So we'll just go ahead and say very little SN2. And so methyl would be by far the fastest SN2 rate, primary the next, and the next, and then this would be by far the slowest SN2. All right, so if we want to write this down, it would be methyl is faster than primary, is faster than secondary, which is much, much faster than tertiary. So this is the rate of reaction for SN2 with various substrates. So sometimes you might be asked, which of these would react fastest with SN2. So the first thing you would want to do is rule out any SP or sp2 hybridized atoms, because those can't do SN2. And then the next thing you would want to do is categorize the remaining sp3 hybridized substrates as methyl, primary, secondary, tertiary, and then think about sterics. So whichever one is the least sterically hindered, which is usually going to be, a methyl or a primary, are going to be the fastest. So methyl and primary, these really, really favor SN2. So a lot of times with methyl or primary, as long as they're not allylic or benzylic, because once we have allylic or benzylic, that's going to start to probably favor more SN1, because that carbocation is going to be so much more stable. Then when we get to secondary, we're really going to see competition. SN1, SN2, and then also E1 and E2, which we haven't discussed yet. But this is where you're going to have to really consider other factors besides just the substitution of the substrate. Is it a good nucleophile and a good base? Is it just a good nucleophile? What's the temperature? Is it a weak nucleophile? All of those sorts of things will come into play. The last thing, so we've got the substrate, basically. That's the first thing we're going to consider. The second thing we're going to consider is the nucleophile. Here we would need a very good nucleophile. And we've talked about what those look like. And then the last thing would be the temperature. And in the SN1 video, I kind of go through a little more description of why this is. So if you haven't seen the what favors the SN1 mechanism reaction video, you might want to go take a look at that one. But basically, low to moderate temperatures favor SN2 over E2. Okay, so when I say low to moderate, it could be a negative temperature, up to maybe something like 40 degrees C. Once we get into reflux temperatures or, high 70s, 80s, 90s, 100s, etc., that's going to tend to favor E2. However, if something is a very good nucleophile and a very good base, a lot of times with secondary substrates, even though we're not given a temperature, a lot of times the questions out there in the book and in other places tend to assume that's going to be an E2 favored, because proton transfer is going to be faster than what we're doing with an SN2. The other things to consider, of course, the leaving group. We do need to have a good leaving group. SN2 does tend to work better when we have a leaving group that is already ready to be a leaving group. So not like when we have perhaps an alcohol that needs to be protonated, etc. And looking at solvent, technically, a polar aprotic solvent is the best. But you will see SN2 run in things like alcohols, or E2 run in alcohols, where it's basically you've deprotonated that alcohol in situ, and so you're using that alcohol as a solvent kind of out of convenience, or maybe because it's safer. So you will see other things, but, if given the choice, you want to try to make a reaction work better with SN2 and it's not working well, then going to a polar aprotic solvent and not a protic solvent would be better.